Let's take a look at the last paragraph of this chapter, which is still about multiplying and adding with powers. Well, it's more about powers in general right now. We're going to take a look at what happens when we have negative exponents. To explain this a bit, I'm first going to explain or take a look at this table right here. We now know that 2 to the 5th power is 32, right? That's 2 times 2 times 2 times 2 times 2. 2 to the 4th is 16, 2 to the 3rd is 8, 2 to the 2nd is 4. And there are some places in this table which are yet to be determined. If you take a look, you see that every step to the right, what happens is I divide by 2, you could say, right? Because every step to the left is times 2 extra. This is 2 times 2, this is 2 times 2 times 2. So if I want to go back, I divide by 2. Can you now fill in this table? Do you think there is some kind of pattern here? Luckily for us, there is. The pattern is that every step you go to the right, you divide by 0. Or by 0, by 2. Never divide by 0, right? You divide by 2. That means that 2 to the 1st power must be 2. And strangely enough, maybe, you'd think that 2 to the 0th power would be 0, but that's going to be 1. Hey, then 2 to the power of minus 1, it's a half. 1 divided by 2. And 2 to the 2 to the power of minus 2 is going to be 1 over 4. This is going to be 1 over 8. As you can see, maybe you see that pattern evolve here as well. Here, 2 to the 1st power is 2. 2 to the negative 1 power is 1 over 2. So that 2 is going to be in my denominator. 2 to the 2nd power is 4, 2 squared. 2 to the power of minus 2 is going to be, hey, this one in the denominator. Here, this 8 is now here in the denominator. This is a pattern that we can always use. There are two major things that you should remember when we're going to take a look at powers with a negative exponent and when the exponent is 0. And in this case, the book already explains this using the number a. So for any number a, as long as a isn't 0, the rule is a to the 0th power to the power of 0 is 1. So 6 to the power of 0 is 1. 1000 to the power of 0 is 1. 2 to the power of 0 is 1. Doesn't matter which number is right here, as long as it isn't 0. 0 to the power of 0 is a bit complicated, so they leave that out here. Some mathematicians say that's 0, some say it's 1. So we don't take a look at what happens when this number here is 0. But when the exponent is 0, then you get 1. Right? 1, 2, 3, 4 for every number a as long as it is 0. If you have a negative exponent, you can now calculate your answer by just doing as if this was a positive exponent. 2 to the 3rd power is 8. Right? And then say, well, it's not 8, it's 1 divided by 8. 3 to the power of minus 2 is in that case 1 over 9, because 2 squared is 9, and now it's 1 over 9. 4 to the power of minus 2 is going to be 1 over 16, because 4 squared was 16, so I get 1 over 16. Etc. And this is the mathematical rule that you can now state using letters to make this a general rule. For any number, and again, as long as a isn't 0, you can say, well, if I have a to the power of negative n, that's the same as 1 divided by a to the power of n. For example, here it was 2, right? So 4 and 2. That's the same as 1 divided by 4 squared. 5 to the power of minus 4 is the same as 1 divided by 5 to the 4th power. Okay? So those are the two rules that are going to be the most important during this paragraph, you could say. And in this video I'm also going to do theory B in one go, I think. I think that's going to be a bit quicker. Oh, let's first take a look at those numbers right here. Maybe I do theory B in a separate video. So here 12 to the power of 0 is 1, right? Because it's always going to be 1. If it was 100 to the power of 0, it was also 1. 2 to the power of minus 5 is the same as 1 divided by 2 to the 5th power. It's 1 over 32. And if I want to, I can also go back, right? So if the question would be write it from this notation to this one, then we're searching for which number to a certain power can I write in the denominator. You do this, this is more uncommon though, because normally we would like to rewrite this notation back to a normal fraction. For example, you could say, I find this a very strange example, but indeed 1 is 554 to the power of 0. Yeah, that's true. It's also 2 to the power of 0. It's also 9 to the power of 0. It's also 1 divided by 1. I mean, yeah, it's an example. It's okay. This one is a bit more direct, the same as this one, right? And I think this one is a nice one to take a look whether you fully understand what you are doing. 1 over 3 to the power of minus 2. Remember, if I have anything to the powers of minus something, it's the same as doing 1 divided by that thing to that power. So here I do 1 divided by 1 over 3 to the second power, squared. What is 1 over 3 squared? Yeah, it's the same as 1 over 3 times 1 over 3. That's 1 over 9. And now I have a 1 divided by a fraction. Remember, dividing by a fraction is the same as multiplying by its reciprocal. Delen door een breuk is hetzelfde als vermenigvuldigen door zijn omgekeerde. Dus hetzelfde als 1 keer 9 gedeeld door 1. Dus 1 keer 9 is 9. Right? Let's do theory B as well. For theory B, who do you think that is correct here? Well, I think that only Bob can be correct. Why? Well, just try using calculations. If you just calculate those numbers that I write here, this will be 8, this will be 16. 8 times 16 is 128. Well, 4 to the power of 7 is quite a big number. That's 4 times 4 times 4, and that's 7 times. Yeah, that gives me 16,384. So Senna cannot be correct. Bob is correct, because 2 to the power of 7 is indeed 128. And that brings us to a certain rule when we calculate with exponents. And that rule we kind of already know, but now we're going to use it when we're not talking about a letter as a base. Dus wat gebeurt er als mijn grondtal geen letter maar een getal is? For example, we know that x to the third times x to the fourth is x to the seventh, right? We added the exponents. Well, the same rule applies when I don't have an x there but a number. So 2 to the third times 2 to the fourth is the same as 2. 3 plus 4 as the exponent is 2 to the seventh. Right? And this rule here, that's the same as we do a power to a power. Only now I don't have an x, I have a 2. That's the only difference in this theory. Instead of a letter as the base, we're going to use numbers as the base. Okay, so for example here, I have 4 to the power of 5 times 4 to the power of negative 3. My bases are the same, they're both 4. So which rule can I apply here? Well, if I multiply, then I can, in this case, add, or because this one is negative, subtract the indices, the exponents. So that's going to be like this, which gives me 4 squared, which is 16, right? And why is it now nice to know those rules when working with exponents? Because if you don't have a calculator at hand, you don't know what 4 to the 5th power is mentally. It's going to be a big number. You can try to do it, but it takes a lot of work. For the same thing applies for 4 to the power of -3. It just is much more difficult to now really comprehend what is right here. What does this mean? Well, it's actually the 16. But to find that number, we must use our rules for powers, which in this case, base with the same number. So here, 3 to the power of -1 squared. Remember what happens. In this case, we multiply the exponents. So -1 times 2 is -2. That's the same as this. Theory A of this chapter is 1/9. Here, this one, I would suggest you first do this part. Why? Well, if I'm first, remember, multiplication from left to right can be used here, but because everything is a multiplication, I can switch the order. So I can do them in any what order I want. And if I would start with calculating this first, that would give me a very big number, which doesn't have a nice base and exponent anymore. And then I have to do it times a very small number. That gives me a very, I think, quite hard calculation to do mentally. Well, if I first use the rules for exponents here, 3 minus 4 gives me -1. And 5 to the power of -1 is the same as 1 divided by 5. Yeah, to the power of 1, but that's just 1/5. Gives me 2/5. Right, so sometimes when I only have multiplications, it's sometimes more clear if you use a different order. First calculate this part and then do times this. You may not do this if there was a plus here, right? Because the order of operation do state that you do multiplication before addition. Same here, first do this part. Well, here you should do it because the order of operation say you should first do something in brackets. Well, and there is not something that we can calculate inside of brackets. And if we would first calculate this and then this, then again we get a very big number and a very small number. Instead, first calculate this. That's 2 to the power of -8. Remember, multiply the components because it's a power to a power. Now I have two numbers which have the same base and the same exponents, so I can now subtract the exponents. Gives me this, gives me this, gives me this. Practice makes perfect. I said it a lot during this chapter, but I think certainly here there are small errors that you can easily make. It's also, I think, maybe the most difficult part of this chapter. So if you think, whoa, this is really difficult all of a sudden, don't worry, I think it is. It's also a plus chapter, plus paragraph 8.7. But please still try to do it, because this will help you out enormously in the next years of mathematics. Okay? If you have any questions, again, feel free to ask, and then I will see you again in next lesson.